Okay, this is the example for apparent power and power factor. Okay, so you are given a circuit consists of resistor and inductor connected in series, and then the supply for the circuit is V equal to 10 volt with the angle of 0 degree. So you need to calculate the apparent power for the circuit, right? So therefore, we know that apparent power that we are looking for is actually equal to S, right? So you are given what the information you given here is actually you are given the V value, you are given the R equal to 3 ohm, and then you also given the XL, uh, the inductive load equal to 4 ohms over here. So therefore, from this circuit, okay, we know that you can calculate the value of I, okay. So because you know the value of V, so you can calculate the value of I. So we know that S equal to V I, or S also equal to P plus JQ. Okay. All right. So therefore, we start, right? So S equal to VI, so you can find I by using V divided by Z total. So V is 10 volt with the phase angle 0 degree divided by Z total. So this is our Z total, right? So R in series with the inductor. So therefore you have 3 plus J 4 ohm, right? For the load, for the impedance. So by divide these two value, you got this value, which is this value is actually the current value. Okay, the current value given here is actually mm, in a passive form. Okay, so therefore from here we can calculate the value of power, right? So power is equal to I squared R. So I squared R, this is not, we just take the magnitude of the I over here, so therefore we take 2 over here. So 2 squared times R is 3, so is equal to 12 watt. Okay, this is power. Remember, power P is actually the real power, so that's why we is I squared R over here. And then next, QL is a reactive part. Okay, reactive power. So reactive power can be calculated using I squared XL, right? So therefore, I squared is 2 squared times XL is 4 ohm. So this reactive power is equal to 16 volt ampere reactive. So therefore, you can calculate the S value by using this P plus JQ, which is, we know that S consists of, uh, mm, this is by using the power triangle, right? So this is your uh, P, this is your S, this is theta, and then this is Q, right? So therefore, S equal to P is the real power, and then plus with the um, reactive power, which is QL. So therefore, by a substitute real power and also the reactive power over here, so S equal to 12 watt plus J16, right? So therefore it's equal to, when you convert into a passive form, so it become 20 volt ampere with a degree of 53.13 degree. So this is how we calculate the apparent power. All right, so Okay, so this is the value, the power triangle with the value. So therefore theta equal to 53.13. The reactive power is equal to 16 volt ampere reactive. The apparent power equal to 20 volt ampere, and then the real power equal to 12 watt. So this is another method uh, that we can use to calculate the apparent power, but this is the formula later on when you go to the complex power, because we still not cover the complex power, so therefore just ignore this solution. But this is another solution, but in order to use this solution you need to know what is actually complex power first, right? So next, you are given an electrical devices is rated 5k volt ampere with 100 volt and at a zero point 0.6 power factor lagging. So this is an electrical device rated 5 kilovolt ampere, 100 volt and a zero point 0.6 power factor lagging. So when they said lagging, is that we know that uh, uh, is actually inductive load, right? So therefore, the question is, what is the impedance of the device in rectangular coordinate? All right. So actually, this as a question, they ask you to find the value of impedance, which is Z, right? Okay. The impedance of the electrical device, guys. So uh, this is, we know that this is a power because the unit is kilovolt ampere, so we know that this is apparent power, right? So therefore uh, uh, we can say that S equal to VI, right? Okay, so V is given over here 100. Okay, so therefore by S also given, right? So therefore you can find the value of I equal to S divided by V. So therefore 5k divided by 100, so you got a 50 ampere. So this is the value of the current by considering the magnitude only, right? Okay. So next step, okay, you are given a power factor. Power factor equal to zero point 0.6. So that's mean cos theta equal to zero point 0.6. So therefore theta equal to cos negative 1 zero point 0.6. So theta equal to 53.53.13 degree. All right. So we know theta, and also we know the current. So therefore we can find the impedance of the device. Okay. So it is good if we can draw the mm, power triangle. Okay. So therefore from there you can see that S is equal to, this is your S, this is your uh no, this is your P, and then this is your Q. I think this is not involved, this thing, this power triangle, right? So like it's okay, just for your reference. So therefore this is the theta, that theta we already calculated. So theta equal to 53.13 degree, and then you know the S value. Okay, so next our step is actually to find the value of ZT. Okay, because actually we want to find the value of ZT, we not find the value of real power or reactive power. So it's just enough for us to know the value of V and I, right? Okay, so since the power factor is lagging, so it's mentioned in the question the power factor is lagging. So the circuit is predominantly inductive. We know that when inductive load usually I V leads I. Okay, so or you can say I lags V. Okay, so therefore due to V lead, so usually your V is given if you are using a passive form, V magnitude is 100, and then we can say that the phase angle is 0 degree, and then theta we know that is 53.13. So I, the magnitude of I is 50 ampere, so we can say that I equal to 50. All right, due to the we know that I lags E, so therefore the magnitude of the phase shift for the current will be negative 53.13 degree. Right, negative here means that we know that I lagging the V, so at this point V leads the I. Okay, so therefore I in a passive form it can be given of this value. So and then we know this V value, so automatically you can find the value of Z total. Alright, so by using this formula, Z total V divided by I, so 100 volt with a phase shift 0 degree divided by 50 ampere with a phase shift negative 53.13 degree, so you got 2 ohm with a phase shift 53.13 degree. So we convert this into a rectangular form. So this is what you got. You got 1.2 plus J 1.6 ohm. Right? So this is our impedance value. So impedance value consists of inductor and also resistor. Alright, so this is another exercise. So you are given a series connected load. Uh, you are given a question. A series connected load draw a current I of t equal to 4 cos 100 pi t plus 10 degree ampere when the applied voltage is given with V of t equal to 120 cos 100 pi t minus 20 degree volt. So you need to find the apparent power and the power factor of the load. All right, a series connected load draw a current. Okay, so that's mean, so you have a load over here. Okay, so the value of I here is given by this, and then the value drop at your load over here is given by this. So remember, this is a time domain, right? Time domain, usually this is a V maximum value. Okay, so this one also a maximum value. Okay, it's okay. So apparent power is RMS value, guys, right? Apparent power S is actually VRMS by RMS. Okay, so therefore S equal to VRMS IRMS. Uh, so automatically this is V maximum, this is I maximum. So therefore V maximum, okay, because we want it in a RMS value, so we know that RMS value equal to VRMS value equal to V max divided by Z2. I RMS value equal to I max divided by Z2. So that's why you have this one, right? So therefore by times your VRMS with RMS value, so apparent power is uh, equal to 240 volt ampere. Okay, power factor is equal to cos theta V minus theta I. right? So this is theta I, right? So this is theta V. So theta V minus theta I, which is negative 20 minus positive, minus 10. So you got cos negative 20, negative 30 equal to 0.88. Okay. Okay, please use your calculator to calculate this. And then we know that is leading, right? So because, right, because cos, you got cos, you got theta, sorry, you got theta V minus theta I equal to negative 30 degree, right? So this is equal to negative 30 degree. So remember, when theta V minus theta I is negative value, so therefore we know that your load is a capacitive load, right? So we can say the power factor will be a leading power factor. Okay, so therefore power factor equal to 0.866. Okay, so the power factor is leading because the current leads the voltage. All right, so therefore the impedance value is equal to V divided by I, right? V is the passive form, in a passive form, which is 120 with a phase angle negative 20 degree divided by I, which is 4 with a phase angle of 10 degree, right? So therefore you got equal to 30 with a phase angle negative 30 degree. So if we convert this one into a rectangular form, so you got Z equal to 25.98 minus J 15 ohm. So you can see here, you got in imaginary part, you got a negative value because we know that the load is actually a capacitive load. So to confirm your answer, right? So leading factor, power factor, usually you got a negative value for the um, reactive load, right? For the reactive part. So therefore, uh, uh, okay, the question is actually to find the apparent power and the power factor of the load, and then determine the element value that form the series connected load. Okay, so next question actually determine the element. We know the element is actually the capacitor due to you got it a leading power factor. So therefore you need to find what is the value of the capacitor, right? So um, by considering this part, right? So this is actually Z equal to R plus JXC or minus, right? So you got minus negative JXC. So therefore we can say that uh, XC equal to this is plus, right? So because it's plus, XC equal to negative 15, okay, right here over here. And then uh, is equal to negative 1 or negative 1 over omega c. So therefore you can calculate the c value. Okay, you can find the c value equal to 1 uh, negative negative, so is eliminate each other. So therefore c equal to 1 divided by 15 omega. So just plug in the omega value in here, which is our omega equal to 100 pi. Alright. So therefore 1 divided by 15 times 100 pi. Okay, so equal to 212.2 microfarad. Okay. So this is the uh, answer for the part B, which is determine the element value. When they say element value, so that's mean we know that from the part A, the element that we are looking for is a capacitor. So therefore C equal to 212.2 microfarad. Okay. So there's a lot of example over here. Maybe you can go through some of the example over here. All right. And then, okay, maybe we can finish this example. And after that, we continue our complex power with a differentiation. Okay. Okay. So, uh, uh, you are given an example over here. An industrial load consume 88 kilowatt at a power factor 0.07 lagging from a 480 volt RMS line. So the transmission line resistance from the power company transformer to the plant is 0.08 ohm. Let us determine the power that must be supplied from by the power company under the present condition, right? And if the power factor somehow change to 0.9 lagging. So this question asks you to find the uh, power that must be supplied by the power company if you are given this specification. And then let's say if they change the power factor to 0.9, so you need to find what is the new power that must be supplied by the power company, right? So if I can translate this one into a diagram, so you can say that this is our uh, this is a whole system. This is a big system, but I represent it this way. So this is a load. Okay. And then they said here the transmission line resistance from the power company transformer to the plant is 0.08. When they say transmission line, so that's mean this is a wire. Wire is a transmission line from supply to the load. So therefore at the transmission line you have 0.08 ohm resistance. Okay. So therefore we can represent a resistance up here 0.08 ohm. Okay. And then the specification here is actually the load specification. All right. So P load is given by 88 kilowatt, and then the power factor for load is 0.07. And then the lagging, when they say lagging, so that's mean the load is a inductive load, right? When they say lagging, so that's mean V leads I, or I lags V. So therefore is an inductive load, right? So please refer, if you don't understand, please refer to the notes. Okay. And then you are given a lagging from a 480 volt RMS line, right? So the voltage here equal to uh, V equal to uh, 480 RMS value, right? So therefore, we want to know what is the power that must be supplied by the power company. So we want to know what is the power over here. Okay. So that's mean we need to know the total power lah. Power supply is a total power, and then you have a power over here. Okay, due to the transmission line, with the transmission line have a 0.08 ohm. Okay, so therefore RMS value for the load can for this system, because this is only a series normal series circuit, so therefore this IRMS equal have an equal value throughout the circuit, right? So throughout the system, so therefore IRMS equal to okay, how we got this one. So remember, P equal to VRMS IRMS cos theta V minus theta I, which is cos theta V theta I is a power factor. So you got the RMS value, so you got the power factor value, and then you got a P value, so therefore you can find the IRMS value. So therefore IRMS value equal to P divided by power factor times VRMS. So therefore IRMS is equal to 259.3 ampere RMS value. Alright, so therefore a total power supply, like I said, is actually consists of this power and this power at the load. So therefore PL is given. So P at the resistor you can calculate, because we already know the current. So therefore P at the resistor is given by I squared RMS times the resistive value over here 0.08. So 88K plus 0.08 times 259.3 squared. So therefore P supply, right, equal to 93.38 kilowatt. Okay, so this is the uh, uh, power that must be supplied by the power company. Okay, so in order to you to understand, I represent all the statement over here in a form of circuit. So this is the power, let's say this is the power company, this is the load, right? And then this transmission line, right? So therefore we can say that power supply equal to power at the load and power at the transmission line, so therefore is equal to 93.38 kilowatt. Okay, so therefore for the question B, if the power factors is somehow changed to 0.9 degree, that 0.9 and lagging, right? Okay, so therefore you can calculate the new value of the power supply by substitute the power factor, right? So therefore the new IRMS value need to be calculated. So this is your new IRMS value. So similar with the previous example, so uh, s- uh, PS equal to PL plus P at the resistor, power at the transmission line, actually this one. Okay, so therefore the new power need to be supplied if the power factor increase to 0.9 is equal to 91.32 kilowatt over here, right? So you can see here, if the power factor is higher, okay, we can say that the power that we need is less, right? So that's why it is very important, like you need the power factor is equal to 1, so therefore we use less power, that's mean less bill, right? uh, okay, so hopefully you can relate that. Okay, for the complex power we can go to the next lecture. So for today, we just go to the apparent power and also the power factor. Okay.